Hello there, ladies and gentlemen. Today we're going to talk about how to solve equations that have rational expressions in them. Basically, what we're going to be looking at is, instead of graphing, we did two variables, rational functions, graphing, all that stuff. These are one variable equations, okay, that we're just going to be solving for x, okay? And the way that we're going to do that is by using some tricks and things that we already know in order to solve these. So take a look at number one here. This is an equation, has rational expressions in it. We have 1 over 2x, we have 1 over 5x. The way we're going to solve this is actually by utilizing a technique called clearing out the denominator. Now, you guys actually know this technique. You probably used it last year. We used it earlier in the year, where you're going to basically find a common denominator and multiply every term by that to cancel out all the denominators and leave you with an expression that doesn't have those things in the denominator. So for example, when I look at number one here, a common denominator for 2x, 10, and 5x would be 10x, right? All of our denominators go into 10x. So I'm going to multiply each term by 10x. And so I'm going to end up with 10x over 2x plus 30x over 10 equals 10x over 5x. And then I'll just simplify each of these fractions. You notice a lot of your variables will actually cancel out when you do this. So over here, the x's will cancel. 10 divided by 2, that's going to become 5. Okay, over here, 30 divided by 10 is going to become 3x. And then over here, the 10 divided by 5 will become 2. And then I solve for x. I subtract 5, I get 3x equals negative 3. Divide by 2, just solve like normal from this point forward, and we get x equals negative 1. Okay, same process we would have done before, solve, do all that, great, all right? Next problem is another one. Sometimes with these rational expressions, what you'll end up with won't be a linear equation like we got here. Sometimes you'll end up with a quadratic, which lucky enough we actually know how to solve because we've already done that in our course. So let's go ahead. X squared x, and this one would have a denominator of 1. The common denominator for these would be x squared. All of those go in x squared. So I'll multiply each term by x squared. And I'm going to go ahead and do my canceling here. So x squareds will cancel. 1x is going to cancel out, and this won't cancel. So I'm going to end up with 5 equals 6 minus x squared. Or 6x minus x squared. Sorry, whenever x is left over. And then what we're going to do is we're going to move these two terms over here. So we get our quadratic set equal to 0. So we get x squared minus 6x plus 5 equals 0. Again, if we have a set equal to 0, we now can use the zero product property. Factor, use zero product property to solve. And this one's going to factor into x minus 5 and x minus 1. And now we can use that zero product property. Two things multiply to give me 0. So x equals 5 would be an answer, and x equals 1 would be an answer. Okay? Again, techniques you already know. This finding the common denominator, clearing out your denominator by multiplying by them. Something you've used before. We just now will have variable expressions we'll do that with, and we'll go through and we'll solve. So everything from so far that we've talked about should look kind of familiar, nothing too crazy. Where this is going to get a little bit different is when we have one extra thing we have to do when we solve these, and that is we have to check for what's called extraneous solutions. I did not do that for these, but if this was on a test or quiz, you would have to do that. But we're going to see in this one why we want to make sure we do that. So, Mr. Guy, what do you mean by extraneous solutions? Well, first of all, you're still going to go ahead and solve this by finding that common denominator. So in this case, I'm going to multiply everything by x minus 2. We'll then go through and we'll simplify and solve like normal. So here the x minus 2's cancel. Here the x minus 2's cancel. So I'm going to get 5x equals 7 times x minus 2 plus 10. I'll then go through and solve this. So we distribute. We get 5x equals 7x minus 14 plus 10. We'll move this 7x over to this side by subtracting it. I'll also go ahead and combine these like terms while I'm doing this. So I'm going to get negative 2x equals negative 4. And then I'll divide by negative 2. and I'll get that x equals 2. All right, cool, Mr. Guy, you did all that, you solved it. What's this thing you're telling me about extraneous solutions? Well, with rational equations, we'll sometimes end up with an answer that we solve for and looks like an answer is actually not an answer. Because you can actually think back to the fact that the function versions of these are not continuous, right? They have places in their domain where we have discontinuities. If the thing I solve for happens to be located in where the function version would have a discontinuity, it is not really a solution. It's what we would call an extraneous answer. It looks like a solution, but it's not. The way I find that is by plugging it back into the original equation. If I plug it back in and it ends up making me divide by 0, then it is an extraneous solution. And we can see that, just like here, it says x minus 2. If I plug 2 in there, I'm going to be dividing by 0, and that's a problem. That's going to make this extraneous. So x equals 2, that is an extraneous solution. Okay, and I would label it as such. And what that means is that actually is not an answer to our equation. So for this problem, there actually are no solutions that make this true. Nothing will make this equation true because the only one that looks like it does is extraneous. It makes it divide by 0, and we can't have that. All right? All right, so that is solving rational equations. Thank you all for watching.